this is another one that falls under the series heading, except this is the geometric formula. So it's another one that's not officially a proof, but it sort of behaves like a proof because it's the same every time. So same steps. So prove that it's true for n equal to 1. So on the left hand side, n equal to 1 means the first term, and the first term on the left hand side is a. So we're trying to prove that for n equal to 1, the left hand side equals the right hand side. So on the right, I'm going to make the n equal to 1. The only n that's there is up here in the power. So that's a equals, and the 1 minus or cancels with the 1 minus or, leaving me with a. So therefore, it is true for n equal to 1. Okay, so step 2 is our assumption. Sorry, I shouldn't write that. So state what the assumption is. Assume that it's true for n equal to k. So it becomes a plus a or plus a or squared. And then here I have a or to the n minus 1, so that will become a or to the k minus 1 because n is k. And on the right hand side I have a times 1 minus or, it was to the power of n, so now it's to the power of k over 1 minus or. So that's our assumption. Step 3 then is based on the assumption to prove that it's true for n equal to k plus 1. So again, same as the other series one. You write it out again. You keep the k term. I'm going to keep this term, and I'm going to add on the k plus 1 term. So it's going to be k plus 1 in place of the k, and then I still have a minus 1. Okay, and I'll tidy that up in a minute. And that's a times 1 minus or to the k plus 1 over 1 minus or. So I'm literally just going to write it out again to tidy this bit up. So it's a plus a or squared plus the term where n equals k. Now this is going to become, so k plus 1 minus 1, the plus 1 and the minus 1 cancel, so it's just k. And then this is a times 1 minus or to the k plus 1 over 1 minus or. Okay, so same as last time based on the assumption. So this bit here is the same as this bit here, and this bit here is equal to this yoke. Okay, so I'm going to replace this with a times 1 minus or to the k over 1 minus or, and that's based on the assumption. And we add on a or to the k. I'm going to try and prove that this is all equal to this yoke here. Okay, so we're going to manipulate what we have here and try and get it to equal what's in the yellow box there. So I think a common denominator first, which would be 1 minus or. Divide 1 minus or into 1 minus or, you get 1, and then multiply that 1 by the top line, so it won't change it. So it's just a times 1 minus or to the k, plus 1 into 1 minus or is 1 minus or, and multiply that by this, you get a or to the k times 1 minus or. Now if there was a common factor there, I'd take it out, but there isn't. So I think the only option is just to multiply out. So a by 1 is a by the minus or k is minus a or to the k. A or to the k by 1 is plus a or to the k, and then a or to the k by minus or is minus a, and it's or to the k or to the 1. And that's over 1 minus or. So these here cancel. This is a, which is fine. Now this part here, So we have r to the k multiplied by r to the 1. So the first rule of indices says that we can add those. So it's k plus 1. Okay, so we have the a, and then instead of r to the k, r to the 1, we have r to the k plus 1 all over 1 minus r. And I'll just remind you what we were looking for. So this is what we're looking for here. So if we take the a out as a common factor, divide the a out here, you get 1 minus divide the a out here, you get r to the k plus 1. And that's all over 1 minus r, which is exactly what the right hand side is. Then you write down your final step, which is your proposition. Let's enlarge that a bit. So the proposition is true for n equal to 1. If the proposition is true for n equal to k, then it is true for n equal to k plus 1, and therefore by induction is true for all n is an element of n, natural numbers.